recording here, and then we will officially start class today. Adjust my chair here. Okay. So we're this is the last full week, right, of the term. So but we do have class next Tuesday. And so we'll still have class on Tuesday, a week from today, but that's also the day that the test number 3 will be posted. So that's just so that's the last regular class day. And then we don't have class during the final exam period, but the which is May the 11th, but the of course the test will be posted then, the final exam will be posted then. But we don't really have have a Zoom meeting on that day. I've already posted, there's an announcement about that here on WebAssign. The sample test for number 3 is already posted. So I sent an email about that last week. So the answers will be posted sometime, probably by Thursday. And then I will also make a video about test 3. Madison says her review for that will be on Monday, okay, during her, I guess at 12, right, during your, coinciding with your regular SI session on Monday. But she also has an SI session on Thursday at 9 as well, her regular SI session. So I hope people will take advantage of that. I know some people came to the SI session prior to taking the makeup and last week, and that seems to have helped. So please take advantage of Madison this week, since we have a little bit of time. We don't have much time left, but we still have new material that we're covering. So I think Madison's really particularly important this week to help you prepare in this brief period before test number 3, and then also before the final exam. And she already mentioned, but we'll repeat this, that her exam review will be on May the 7th. But we'll repeat that. And there will be a review posted for the final exam next week, probably on Tuesday of next week, the last class day. And so there is a final exam review, but part of the sample number 3 test is also problems that would be on the final, but not on test number 3. So when you look at the sample test number 3 at the end, there's a section that's marked off and said these problems are covered on the final exam, but will not be covered on test number 3. Okay, so that's even more preparation you can have for the final exam. So there's quite a bit of homework, right, that we have to do, stuff that's due on Thursday and at the end of this week, and then stuff due next week, and then at the time of the final exam is when this last homework is due. Actually, it's due when the final exam is due, right? The very last homework. And then there's homeworks due next week on integration, which we're talking about now. Some of which would be on the test number 3, and but this is an optional homework, right? Remember that homework is optional, so the list is not quite as long as it looks. I've tried to make these as brief as possible, so I've shortened the homework as much as I thought I could, so to keep it doable, right? But it will be a lot between now and May the 13th, right? When you have to turn. When all this is due, and I have to actually submit grades. So that's when we're, we're completely out of time there. Do you have any questions about some of this, just the schedule stuff that I mentioned, of what's going to happen over the next couple of weeks? Any questions in particular? Any homework questions that you want to ask here in class? So again, Madison, I know, was going to go over first derivative and second derivative test. Remember, these are very similar to each other. And that's certainly covered on test number 3. So a big piece of test number 3 will be about the first and second derivative tests, right? A little bit about limits, but those homeworks have already been those homeworks have already been done, already due, right? So they're kind of off our radar now, but that will also be on test number. That will also be on test number 3. All right, so y'all aren't jumping up and shouting questions at me. Okay, so so I'm going to take it that you're comfortable with things, or maybe just haven't really looked at things that closely yet, right? But make sure you start on that quickly, because this is an important homework and it's due on Thursday, right? So that's definitely going to be important to your test number 3 score. Okay. All right, so today we're going to continue talking about integration, and that's so you can think of that as the reverse of differentiation. So we're just going to sort of take our all of our differentiation knowledge, right, and kind of run it backwards. And so since y'all are pretty skilled now at differentiation, it makes this process a lot easier. And today, at least, we'll see one application of why being able to do differentiation in reverse is important. And then hopefully by Thursday, we'll get to see other instances of why integration, which is that reverse differentiation process, that's the name of it, why that's useful and why that's important, okay, to be able to do that. So I'm just going to launch into the notes where we were last time. Okay, I think no, not these notes. These notes. All right. So we were just going through some examples, right, of going through this integration process, or this, you can also call it anti-differentiation process, but that's a mouthful, right? And one thing to recall, right, is that there's some kind of special symbols, right, that is associated with this process. This elongated S, which is, a very familiar symbol because it's so unique to calculus. This is called an integration sign, and it's used to indicate this integration process. So when you write the integration sign here, and then a formula for a function, and then you usually terminate this expression with this dx notation. Although this does have mathematical importance, for us, you can sort of just think of it initially here as just terminating this integration expression, right? Okay, when you write all of that down, then that just indicates that what we're doing here is finding the antiderivative, right, of this formula 1 over x cubed. So this represents a function, right? This expression represents a function, or you can think of it, it represents a formula or an expression whose derivative is 1 over x cubed, right? So up until this time in the course, I would have given you a formula like 1 over x cubed, and I would have said, find the derivative, okay? And so you would have, we have rules for doing that, right? You can all do that now very successfully. But now when we use this notation, right, what we're doing is just the opposite, right? I'm trying to find a function whose derivative is 1 over x cubed, right? And we actually went through this example last time, and we found that that formula turned out to be minus 1 over 2x squared plus some constant. Remember, antiderivatives are not unique, so functions can have lots of different antiderivatives, and you can form a new antiderivative for a function just by adding a different constant. So this c represents a constant. You can just add a different constant to your formula, and you'll still have an antiderivative for the function. So that's one thing that's a little bit tricky about antiderivatives as opposed to derivatives, right? If I give you a function and I say find the derivative, you're going to find one and only one answer to that, okay? But if I give you a function and say find its antiderivative, then there are lots of different possibilities there, because we can change this constant. This is a constant right now, so it's a number added at the end, and that would give us a different antiderivative. Okay, so to find this antiderivative now, we used a formula, we used a rule, and it's kind of the a reverse of the power rule. And so and since we use the power rule a lot to calculate derivatives, right? That's a really important formula in finding derivatives. The so-called anti-power rule is going to be an important formula in finding anti-derivatives, all right? So you don't use it all the time, but we use it a lot, okay? So when you're trying to find the antiderivative, or when you're trying to integrate a power of x, right? So if this formula here that's behind the integral sign, by the way, this is called the integrand, all right? So this is the integral sign, this is the integrand. So if you're integrand, if the formula you're trying to integrate is a power of x, and this can be virtually any power here, so it can be a fraction too, all right, or it can be a negative power, then the anti-power rule says, okay, it's easy to find this antiderivative. We're just kind of run the power rule in reverse. And when you run the power rule in reverse, what you do is add 1 to the exponent instead of subtracting 1, because that's what we do in the power rule, right? You subtract 1 from the exponent. Here we're going to add 1 to the exponent, and then we divide by that new exponent. Okay, so it's a really very simple a rule, just like the power rule is a very simple rule. And then remember, you can have lots of different antiderivatives, so you get a different antiderivative just by adding a different constant here. So we always indicate that just by putting plus c. This c represents any constant that we choose, right? So this could be +1 or +2 or plus the square root of 3 or whatever, right? Okay, and that would still give us a valid antiderivative for this power of x. I said virtually any exponent can be used here in the anti-power rule, except one exception, which is -1. So if you're trying to integrate x to the -1 power, which is 1 over x, which is a very familiar function, right? So that's something that we might want to be able to integrate. You cannot integrate that using the anti-power rule, okay? Because of course what happens is if the exponent here is -1, well, when you add 1 to -1, you get 0. So you would have x to the 0 in the numerator. I guess that's okay. But in the denominator, you would be dividing by 0. And of course, you cannot do that, right? So the anti-power rule breaks down when this exponent is -1. And that leaves us a big mystery, as I mentioned last time, is what is the antiderivative of 1 over x to the -1 power? And well, we're not going to actually find that out this semester. So we're going to leave a little bit of a void here. In that case, that is where calculus 2 will start, is trying to determine what is the antiderivative of x to the -1 power. And it turns out to have a very important and interesting answer. Okay. All right. So there's kind of just our really quick review of integration. We don't need much of a review because it's really just that easy. So let's take a look at another example here. Where we're going to get a chance to use the anti-power rule, right? So I want to integrate x over the square root of x, all right? So remember, what this big expression means is I'm trying to find a function. So I'm going to end up with a formula here. Your answer is not going to be a number. You're going to end up with a formula here. And that function, right, that you get when you take the derivative of that new function, you should come up with x over square root of x. All right, so now this is not, x over square root of x is not a power of x, right? If that were just x to the first power, that would be a power of x. So if we just had the numerator here, that would be something we could integrate, right? Or if we just had square root of x, that would be a power of x. So we could integrate that using the anti-power rule. But x over the square root of x is a little bit complicated. That's not just a power of x. So the anti-power rule here does not quite apply directly, but that's okay. We're going to fix the expression to make it apply, because let me point out that you can divide x by the square root of x. When you divide x by the square root of x, notice you get square root of x. So x over the square root of x simplifies to just square root of x. And that is a power of x. So we can integrate this using the anti-power rule. But we just had to cheat a little bit and simplify x over the square root of x. By the way, why is x over the square root of x? Why does that reduce to x? Well, there are lots of ways of thinking about that. But one way of thinking of it is, remember, x is the square root of x times the square root of x, right? If you multiply square root of x times the square root of x, you're going to get just x, right? That would be like square root of 2 times the square root of 2 is 2, or square root of 5 times the square root of 5 is 5. Well, square root of x times the square root of x is x. So if you rewrite x as square root of x times the square root of x divided by square root of x, of course, one of these square roots of x will divide out, right? And so you get left with square root of x. But square root of x, as we all know and love right now, by this point in the semester, is the same as x to the 1/2 power. So that is a power of x. And now we can integrate that, right? We can find its antiderivative using the anti-power rule. Now, one thing students like to confuse, I'm not quite clear why this is the case. I guess it's just not enough practice. But one thing students like to confuse is the power rule and the anti-power rule, okay? So students will frequently write the answer to this question as they will subtract 1 from the 1/2, and they will bring the 1/2 down. So they will write the answer as 1/2 x to the 1/2 minus 1 here. They're using the power rule, right? But the power rule is for differentiation. We're not differentiating here, we are integrating. So be careful about when you're integrating and when you're differentiating. Obviously, there's a difference there, okay, right? So don't do one when you're supposed to do the other. The integral sign is the clear symbol, right? We're trying to integrate here. We're trying to find the antiderivative here, not the derivative. So the power rule is the wrong way to go. It's the anti-power rule is what we want to use. So how does the anti-power rule work? Well, it works in reverse. You're going to add 1 to the exponent, right? Instead of subtracting 1 from the exponent. And now you divide by your new exponent. And don't forget there, this is just kind of a reflex. You have to add the constant, all right? So you just sort of do that automatically when you're finding an antiderivative. So let's see, well, what is 1/2 plus 1? That is, that's 3/2. So you have x to the 3/2 over 3/2. Now, one thing you have to remember frequently when you're using the anti-power rule is what happens when you're dividing by a fraction. Remember, when you're dividing by a fraction, that's the same as multiplying by the reciprocal. So if you're dividing by 3/2, that's the same as multiplying by 2/3. So you can rewrite this as 2/3 times x to the 3/2 power. Don't forget the constant there. That's really already a pretty good answer. But if you want to convert this back to radicals, you can do that. So this is 2/3 times, what does 3/2 power mean in terms of radicals? Well, remember the 2 in the denominator tells you this is a square root. So you're going to get a square root here. And then the 3 stays as a exponent. So you have 2/3 times the square root of x cubed plus a constant. You actually can simplify square root of x cubed a little bit, but I think I'm going to leave it like this. This is pretty good already. All right, so just going to leave it like that. So there's our anti-derivative, 2/3 times the square root of x cubed plus a constant. So what do we know about that antiderivative? We know, or what's supposed to be the case, right, is when you take the derivative of this, expression, you're supposed to get square root of x, which is the same as x over square root of x, right? So remember, you can kind of check your work when you're doing integration. It's hard to do when you're differentiating, but when you're integrating, you can check your work by taking the derivative of what you get. If you differentiate what you get, right, and that gives you the integrand, what you were trying to integrate, then you got the right answer. Okay, I mean, that's the only relationship between these two expressions. The derivative of this is supposed to be what you started with, right? Okay. All right, so so you see, you can kind of check yourself here to see if you've gotten the right answer. All right, now this next example does not use the anti-power rule, okay? Because now we have a trig function. So this is not a power of x. So this one, we just have to kind of treat by inspection. We just have to think about it. What is the antiderivative? The antiderivative or the integral of cosine of x. So remember, the question you're asking yourself is, what function, when I differentiate it, will give me cosine of x? You're not asking yourself, you are not asking yourself, what is the derivative of cosine of x, right? We're not differentiating here, we're integrating. So you have to ask yourself kind of the reverse question. What function, when I differentiate it, will give me cosine of x? That's how you get the answer here, right? Okay, so you guys know this very well now, right? Because you know, you've differentiated a lot now, so you know what function, when you differentiate it, is going to give you cosine of x, right? Calvin, are you there? Can you just think about that? What function, when I differentiate it, when I take its derivative, will give me cosine of x? Saad answered there. Thanks, Saad. Okay. I'm not sure what Damien put. Is that an emoji, Damien?
Negative sign. I thought it would be negative sign.
You thought it would be what?
Negative sign.
Yeah, so, but all right, so what mistake did you make there, Damien?
No, I had that. Is that what we're...
Yeah, Damien, what you did was you differentiated, right? Okay, because the derivative of cosine of x is minus sine of x. That is correct, all right? But that's the derivative. We're thinking backwards here, okay? So we want to know just the opposite. What function, when I take the derivative, gives me cosine of x? So Damien, can you think of that? Sine, yeah. So you don't need the negative there, right? Okay.
Yeah.
It's just sine, right? Okay, because the derivative of the sine is the cosine, right? We've all got that memorized, right? Derivative of the sine is the cosine. Yeah. So that's how you want to think of it, right? So, but one other thing, one of the little, just you know, kind of little automatic thing there, right? Okay, a little formality is you have to add in the plus c. Okay, so there's the full answer. Yeah. So, and then again, you can check yourself, right? Just think, okay, when I differentiate this, what am I going to get? Well, the derivative of sine is cosine. The derivative of a constant is 0. Great. So we get cosine of x, right? Maybe we have to do that again here. All right. Now, Damien, okay, now I'm gonna put you on the spot again. All right. So now I'm doing the antiderivative of sine of x, right? Okay. I want to do the antiderivative of sine of x. So what function's derivative is sine? Or something close to sine, right?
Cosine.
Cosine, right. So kind of your first guess here would be this has got to be something like cosine, right? Okay, because you know, the derivative of the cosine has something to do with sine, right? So the first thing you would write down here, this is what I would do. The first thing I would write down here is cosine x plus a constant, right? But now let's check ourselves. Let's check ourselves, because we can check ourselves very easily here. What is the derivative of cosine?
Sine.
Yeah, not quite sine. What is it?
Oh, what is it?
Say it's sorry, say that again.
Negative negative sine.
It's negative sine. Unfortunately, when you take the derivative of cosine, you get minus sine. Darn it. And here I have positive sine. All right. Now, of course, the derivative of the constant is 0, so that's all right. But I'm off by a sign, right? Okay, because the derivative, well, SIGN, I'm off by a minus sign, right? Okay, because the derivative of the cosine is minus the sine, darn it. So this is not quite correct, right? I'm off by, how can I fix it though then? The fix seems kind of obvious. What could I do?
Negative cosine.
Yeah, put a minus. Yeah, just put a minus in front of your answer, right? Okay. So now when you take the derivative of, here, I'm going to do it. So there's my notation for taking the derivative. Now I'm going to take the derivative of minus the cosine of x plus a constant, right? So what's that give me? Well, the derivative of cosine is minus sine, but then I already have this minus sign here. So I have minus sine of x, and of course the derivative of the constant is 0. And the minus and the minus will cancel, and yay, I get it, right? Okay, so I do get positive sine of x. So I had to cheat a little bit in my answer and put a minus in front of the cosine, okay? Well, that wasn't too bad, right? Okay, so I did have to use a little bit of logic there, but not too bad to see, right, that I can fix the cosine just by putting a minus sign in front of it. Let's try one more, and then I'm going to show you, I think one more, then I'm going to show you an application. Yeah, okay. All right, so let's try this one. This one looks terrible. Sine of x over cosine squared of x. And that really would be hard if we didn't simplify this, okay? I'm not sure I could, well, in fact, I'm sure I couldn't integrate this without simplifying it. But it turns out that you can simplify sine over cosine squared because, let's see if I do this right. We can write this as sine of x over cosine squared, of course, is cosine of x times cosine of x, right? But what's sine over cosine? Remember from trig?
Tangent.
That's tangent. So what? So the sine over cosine is really just tangent. So I can write this part, I can write as just tangent of x. Now I still have this cosine of x, but it's in the denominator. So I still have 1 over cosine of x. But what's the reciprocal of cosine of x? That has another name. What's 1 over cosine of x? That's another trig function, right? What is 1 over the cosine of x?
Secant.
That's secant, right? So what we really have here, when we wrote sine x over cosine squared of x, what we really had here was tangent of x times secant of x. And so now that, at first, that you're thinking, how's that? You know, that doesn't look very helpful. How am I going to integrate tangent of x times secant of x? That looks terrible. But remember, we're just thinking of what function's derivative is tangent times secant. And I think we know that, right? Okay. Which of your trig functions, when you differentiate, it gives you tangent times secant as the derivative? Just go through your list there. It's not sine, it's not cosine, it's not tangent, because the derivative of tangent is secant squared. So it's not a tangent. Is it secant? What's the derivative of secant? If you take the derivative of secant of x, what do you get? What's the derivative of secant? Did y'all write it down for me? Someone chat it to me. What's the derivative of secant?
Cotangent.
Nope. I've already forgotten this.
Secant?
No, I know you haven't forgotten
Secant?
it. What is it?
Secant?
Well, no, not just secant, Colin. This would be too good to be true if the derivative of secant was still secant. But so what is the derivative of secant? A little bit more complicated than just secant.
Isn't it secant x tan x?
Or...
Yeah, exactly right, Mohammed. That's exactly what it is. The derivative of secant is secant tangent, right? Okay, y'all have already forgot those? Wow, y'all just really flushed that knowledge right down the drain when y'all finish the test, but you can't do that, okay? So
these are some of the stuff we gotta memorize, right? Or...
Right, yeah, you just have to memorize this because it's not clear at all why this is true, right? So I mean, there's a reason why this is true. I mean, you can figure it out that the derivative of the secant is secant tangent, but it's too hard to figure that out without memorizing it. You just memorize it, okay? So the 6 trig functions, you know, sine, cosine, secant, cotangent, cosecant, right? Okay, cotangent. You just got to cosecant, you just got to remember their derivatives, okay? You just have to memorize them. So, you know, whatever it takes to memorize them, just have to memorize that. Okay, so the derivative of the secant is secant tangent, but this is secant tangent. I just have it written in reverse order, right? So you know the answer here, right? Okay, what function's derivative is secant tangent? It's secant. So there is your antiderivative, right? It's secant. And then don't forget to throw in that constant, okay? So that one is tricky just because you have to use your knowledge of trig to rewrite the integrand as tangent times secant, but then you do have to remember, oh yeah, okay, the derivative of secant is tangent times secant. So I know that what the antiderivative here is, it's just secant. Okay, so now let's look at an a application here. All right, because you know, why is finding antiderivatives? Why might that be useful in practice? Okay, all right, so here before we launch into the problem, here in general is a situation that frequently occurs in science. All right, so we have some quantity that we're interested in observing and measuring. Okay, and but frequently in science, we it's easier for us to observe I'm not saying it's easier for us to observe, but we have knowledge of how that quantity is changing, okay, right? In particular, how that quantity might be changing over time, but it doesn't have to be changing with respect to time, okay? So we know how a quantity is changing over time. We know its rate of change, in other words, and then we want to project in the future you know, how large or small that quantity is going to be, right? So we want to take the rate of change of the quantity because we can measure that in some way, or we have some knowledge of that rate of change for some reason, okay? And then we want to use our knowledge of the rate of change of the quantity, right, to project in the future how large or how small that quantity is going to be, right? So that's a perfectly sensible situation that might be occurring, right? Now, if the rate of change of the quantity is steady, then that's easy to do, right? Okay, if the quantity is changing at a steady rate, then it's very easy to project into the future how large or how small that quantity is going to be in the future, right? If it's changing at a steady rate, that's a simple question. By the way, quantities that are changing at a steady rate, right, then the functions that you can use to predict what the quantity is going to be in the future, that's a linear function, correct? Because linear functions change at steady rates. But the problem, of course, in life is that quantities don't change at steady rates all the time, right? Okay, they change at different rates over time. So that makes it much harder, right, to project into the future how large or small a quantity is going to be in the future, right? based on its rate of change currently, okay? Because we know that the rate of change itself varies over time. Let me give you an example here of this before we look at this particular example. So here's a quantity that is really in the news these days, okay? This is of interest to people all over the world, okay? This is the graph of daily new cases of COVID, of course, but this is in India. All right. So there's been a lot of news about the COVID situation in India because, of course, they've been having an explosion of cases in India, and it's very alarming because it's overwhelming their hospital system, right? Okay, and then it's causing a lot of unnecessary deaths. So right here, of course, is a graph of recently, since this is over the entire time of the pandemic, but of course what we're focusing on is right here recently, right, since February. Notice this sharp upward jump, right, in this curve, right, of daily cases, right? And of course what people are interested in knowing, in projecting, is, you know, of course, what's going to happen in the future, right, to these what's going to happen in the future to these number of cases, correct? Okay. Right, because we're trying to project, you know, how bad is the situation going to get with respect to, you know, the hospital system or deaths, correct, right, from these COVID cases. And of course, this is a difficult question, right, but it's an important question for us, correct, okay? And again, these projections are difficult to make, right, because the number of new cases in an epidemic is not steady, okay? Right. Okay. As time goes forward, right, the number of the rate of change of these cases is itself going to change, right? Okay. And why does that happen in an epidemic? Well, of course, when the when the number of cases is increasing and people become alarmed, right, people's behavior change. They become much more cautious, correct, right? So the rate at which the infection is spreading slows down. Governments take mitigation measures, right? So they enforce things like lockdowns, right? So that also changes the rate at which the infection is increasing, right? So, and then of course you have less of the population. As more people get infected, there's less of the population that is vulnerable to the being infected. So that also slows down the infection, right? So the rate of change there just is not steady, right? Okay, in the future. So it makes these projections of how this curve is going to behave in the future, right? How these cases are going to continue to increase, or if they start to decrease, difficult to project. One of the things you may have already noticed here, so we hope this is true, right? Right at the end of this curve is, notice the curve appears to be trying to form a peak, right? Okay, so it looks like there may be a turning point coming up here in the curve, right? Okay, that would be good news for us, correct? If there's a turning point. And so people are very interested in projecting, where's that turning point going to actually be? When is that going to occur? This is what epidemiologists do for a living, right? Is trying to project, when is this turning point going to occur, or if it's going to occur. Another thing that appears to have happened in the curve, right, is there's an inflection point, right? Okay, maybe right about there. See where I'm pointing the cursor there? Right about there, there appears to be inflection point. The concavity has changed. Wow, that's really great for us, okay? Because this part of the curve is concave up. That means that the speed of the infection was increasing here. Okay, so the infection was actually spreading more rapidly until maybe this inflection point, and now the speed with which the infection is spreading, although it's still spreading, has decreased, right, or is now decreasing, right? Okay, so that inflection point is also very useful to us, right, to see here on the curve. So we don't know in the future, right, what's going to happen, but we do have information currently, and we know how epidemics work from, of course, from past experience with studying epidemics. we know something about the rate of change of epidemics, how the rate of change behaves in epidemics. And so we want to be able to use that rate of change to project into the future, you know, what's the epidemic going to look like here in May or in June, right? Okay. So there's an example, a current example, right, of how we often use calculus. We want to, we have information or we have knowledge of how rate of change, the derivative of a curve is working or what it is. Can we use that derivative information to give projections about how the actual curve itself is going to behave in the future? Okay, all right, so there's a current example. Let's look at an example from physics. All right, so so this is a little bit less urgent example, okay, but nevertheless is an important example from physics. So suppose we throw a baseball right up into the air, and it's going to have an initial velocity. We're just kind of making up numbers here, but it has an initial velocity of 64 feet per second. So I'm throwing the baseball up into the air, and when it leaves my hand, right, okay, it has a velocity of 64, I'm sorry, feet per second. So it's going up, because this velocity is positive. So it's going up at a rate of 64 feet per second, right? Of course, it's going to immediately slow down, right? Because gravity is immediately going to impact it. So this rate of change is not steady, okay? That rate of change is not steady, right? But initially it's going at 64 feet per second, and it starts from a height of 80 feet. So we're throwing this baseball up off of a tower or something where we're at an initial height of 80 feet. And the question here is, find the function that gives the height of the baseball after a given number of seconds, right? Okay, so notice we have information here about the velocity of the baseball, right? Okay, when it initially is thrown, but we want to be able to use that information to be able to predict, right, to write a formula so that we can predict what the height of the baseball is going to be at any given time after we throw it, right? So see, where you're going to use rate of change information, right, that we currently have to and a rate of change that's not steady, by the way. We're going to use that information because the ball is slowing down, so the rate of change is not steady. We're going to use that information to be able to predict how high the ball is going to be in the future. Seems impossible, right? Okay, seems like something that cannot be done. Okay, but of course, with calculus, we are going to be able to do this. Now, there's one other little hint you have to know, okay, about the baseball. When you throw objects up in to the air on planet Earth, okay, if you're ignoring wind resistance, we also know what their acceleration is going to be. So because this is how all objects ignoring wind resistance are going to behave under the Earth's gravity. Okay, so this is something that we know universally, and that is their acceleration, which, remember, the acceleration is the rate of change of the derivative. It's the second derivative, correct? Okay, so it's the rate of change of the rate of change. We know that acceleration is minus negative 32 feet per second. It's per second, right? Because this is acceleration at any time. So on Earth, acceleration is constant. It's always minus 32, okay? It's negative, of course, because gravity is slowing objects down, right? Okay. All right. So, or they're pulling objects back to the center of the Earth, right? Okay. Now, how in the world can we use this information to write this formula down for the height of the baseball anytime after it's thrown? All right. So, because it seems like we don't have a lot of gosh, seems like we don't have a lot of information here, right, to go on. But we do, okay? I mean, we have some, right? So maybe there's some hope here. All right, first, we know the acceleration, okay? We know the acceleration. So we know something about, we don't know the formula for this function s. This is the function that's going to give us the height of the baseball after a given time t, right? We don't know much about that, but we know that the acceleration here is minus 32. So what is acceleration again in terms of this function s? What's the acceleration? In calculus terminology, what's the acceleration? Acceleration is kind of physics terminology, right? But in calculus terminology, what's the acceleration?
The first derivative.
No, not first derivative, Van. Close.
Second.
Second derivative. So you know something about the second derivative of this function s. You know that it is minus 32. By the way, it's a constant function, Van, because acceleration is always minus 32 at any time t. Okay, so there doesn't have to be any t in this formula for acceleration. On Earth, acceleration is constant. Okay, it's always minus 32 for any object, by the way, this pin or this baseball or a bowling ball, if you threw it up into the air, if you ignore wind resistance. Okay, the acceleration for any of those objects is minus 32. Okay, so that's kind of a lucky feature of gravity. All right, the acceleration is not determined by the weight, okay, of the object. It's always a constant. It's minus 32 feet per second. Okay, this is in feet per second, not meters per second or centimeters per second. All right, so we know this is minus 32. Now, Van, we know a little bit else about this function s. I want to write it down because, Van, we also know that what's the initial height of the baseball? What were we given?
80 feet.
80. Initial means at time 0. So you know that when t was 0, the height was 80. Okay, the height was 80. Now, in writing down the function s, you have to put in 0 for t because it was at time 0 that the height is 80, right? Keep in mind that the height is changing. So if you change this t value to something other than 0, you're going to get a different number here, right? Okay, that's not true for acceleration though. For any time t, the acceleration is always minus 32. All right. Now we know something else, Van. We know that the velocity was 64 at time 0. When we initially threw the baseball up, it was traveling at 64 feet per second. So how can we write that down mathematically? Here it is written in words, but how can we write that fact that we know the velocity at time 0 was 64? How can we write that down in math?
Is velocity the first derivative?
It certainly is. So velocity is the first derivative. So what do I write down here?
So s.
S,
Like
right?
first, and then 0 is equal
0,
to
right,
64.
is what?
64.
There you go, right, it's 64. So we do have some, we do have a little bit of information to work with, but now I want to write down what's the whole formula for s of t. I want to be able to figure out what is the height at any time t, not just 0, right? So I want to be able to write down this formula for s of t, okay? So I can predict the height of the baseball at any time t, all right? So now, so what I have to be able to do, see, is work backwards from the second derivative. I have to work backwards to the original function because I know the second derivative. So I know what s double prime of t is. I want to figure out what s, without the primes, what s of t is, you see, okay? So normally, well, not normally, up until this point in the course, we have been going in this direction. We would start with the formula and we would write down the second derivative. But now we're so smart, we're going to start with the second derivative and go backwards to the original function, see? Okay, so we're working in reverse. What's that process called, of course?
Antiderivative.
Yeah, anti-differentiation, Alba, you're right, or integration is kind of the short term, although that's not really a short term, right? Yeah, so we're integrating here, right? That's what we're going to be doing. All right, so let's start that off now. So I know the second derivative is well, let me not rewrite this, okay? I know the second derivative is minus 32, right? So let's find the antiderivative. Let's find the antiderivative of the minus 32, which is the second derivative. By the way, here, when you write down antiderivative, you will write dt, not dx, just because we're using t as the input variable here, right? Not x. Wouldn't be a crime if you put x, though. That everyone would understand what you meant. All right. So Alva, when you take the antiderivative of the second derivative, what are you going to end up with?
Constant.
Which derivative?
Of the second, the first derivative.
Yeah, you're going to end up with the first derivative, right? Yeah, you're not going to end up with the original function. You're going to end up, unfortunately, well, I don't know if it's unfortunate, but what you're going to end up with is the first derivative. See, so when you take the second derivative, this one, and integrate it, you're going to get the first derivative back. Okay. Now, once we've done this and found the first derivative, then we can integrate that to find the original function, see, right? Okay. So, well, let's see if we can do this. What is the antiderivative of minus 32? That should be easy. What is the antiderivative of just a constant? So if you have a constant, what function's derivative would be minus 32?
Constant.
No, not a constant. If you wrote a constant here and if you just wrote a constant here and you took the derivative, you would get 0, not minus 32, right? Because the derivative of a constant is 0. But what would give you minus 32? Can you think of that? Let me make it easier for you. If I had 5t and I took the derivative of 5t, what would you end up with?
5.
5, right? Okay. Or if I had minus 5t and I took the derivative, I would get minus 5, right? Okay.
Yeah.
So if I have minus 32 and I want to take the antiderivative, what would that be?
Negative 32t.
Perfect. Yeah, minus 32t, right? You've got it. Nice. Plus, don't forget though, darn it, we always have to throw in that extra constant. Oh, so there is my first derivative. It's looks something like this. It's minus 32t plus some constant. Now I have to figure out what that blasted constant is, though. Okay, because I can't have this vague constant in my formula for the first derivative. So I got to figure out what that constant really is in this case. Okay. Now that I think I can figure out though, because I know that s prime of 0. Van told us this a moment ago. What's s prime of 0? You say I have it up here, right? What's that?
64.
64. Now, look, so I know this has to come out to be 64. If you plug 0 into this formula, though, right, you get minus 32 times 0 plus a constant. So minus 32 times 0 is 0. So guess what the C value has to be? It just has to be 64, right? Okay, because minus 32 times 0 plus this constant has to come out to be 64. That means the constant has to be 64. So you're done. There is the first derivative. Cool. So we knew the second derivative, and we were able then, using integration, to write down the first derivative. There's the first derivative. Okay. Now, so that's nice. All right. Unfortunately, that's not quite enough because I want to know what the original function is, right? Okay. I don't want s prime of t. I want just plain old s of t. So how do you get backwards to s of t? Well, you know its first derivative. So what do you do with the first derivative to get the original function? What's the process called again? Someone typing it.
Integral?
Yeah, integral, exactly, integration. So to find the original function, find the antiderivative or the integral of the first derivative, which we know is minus 32t plus 60 plus 64. And don't forget, you have to terminate this. It's kind of a formality here at first, but you have to terminate this with the dt, all right? Okay, so now we want to find this antiderivative. Let's see if we can do that now. So we have to think about this a little bit. One nice thing about integrals, though, is although you've got two terms here because you've got the plus, you can do this one term at a time. So so let's do it one term at a time. First, let's start with the minus 32t. So I want to find its antiderivative. That is a power of t. That's a power of t. So you can use the anti-power rule. So what does the anti-power rule say? You're going to do what? You're going to do what with the exponent? The exponent here is 1, by the way. So what are you going to do with the exponent?
Add 1.
Add 1, right. So you get t to the 1 plus 1 divided by the 1 plus 1, divided by the 2, okay? Now, go to the second term. What's the antiderivative of 64? That is a constant, though. That's a constant. So we did that just a moment ago, right? When we were finding the antiderivative of the minus 32, right? Remember, we just added the t onto that? Well, that's the same thing with the 64. The antiderivative of a constant is just going to be the constant times the variable. So the antiderivative of 64 is 64t. And then don't forget, got the c that you have to put in. All right, so let's see what this is. This is minus 32 divided by 2. That's minus 16. And then you've got t squared plus 64t plus the constant. By the way, when you take the derivative of this, what do you get? Well, 2 times minus 16 is minus 32, right? So you get minus 32t, and then the derivative of 64t is 64. So we know this has to be the right answer, because when we take the derivative of this, we get minus 32t plus 64. That's what we wanted. So there we have it. There is almost our formula for s, okay? Except we have to figure out what the darn c is, right? That we have that pesky c in there again. But now, I have a little information to help me with this. Because remember, we knew that s of 0 was 80. The initial height of the baseball was 80. So we can make use of that information. I know that s of 0, which by this formula is minus 16 times 0 squared plus 64 times 0 plus this constant, this has to turn out to be 80 because the initial height of the ball was 80. So notice these two terms disappear very nicely. And what is the constant then? It's got to be 80. So now you can fill that in. There is your formula. So this formula will give you the height of the ball at any time. So you can now you can figure out what the height of the ball is going to be at any time after it's thrown. Okay, notice we didn't start off with much information, right? We had how high the ball was when we threw it. We knew what its initial velocity was, so we knew its rate of change. See, we had information about the rate of change, and we just happen to know from physics that the velocity of any object that's under the Earth's gravity is going to be minus 32 feet per second. So that's just a given because that's just a fact from physics. Okay, so just using those little pieces of information, now we have a formula we can use to determine how high the ball is at any instant. In particular, when does the ball hit the ground? So if we want to know when the ball is going to hit the ground, eventually it's going to hit the ground, right? If we want to know when it's going to hit the ground, now we can use our formula. Let's see. So we want to know when is the height of the ball going to be 0, because that's going to be when it hits the ground, right? So take your formula that you discovered and set it equal to 0 and solve for t, and then you'll know when the ball hits the ground. All right, so you can figure out, you can project in the future, right, when the ball is going to hit the ground. Well, that's just a quadratic equation to solve, right? So you can solve that quadratic equation and figure out when the ball hits the ground. I'm not sure what the answer is. 5 seconds, maybe. I don't know if y'all can solve that, okay, by factoring or by using the quadratic formula, okay. All right, see, so there's an instance, but it happens frequently in science where we know information about rates of change, and then we want to use that of a quantity, and then we're going to use that information to project what the value of the quantity is going to be in the future. In this equation, by the way, that we started off with, the s double prime of t equal minus 32, notice that is an equation that involves the derivative of this function s, right? We wrote down this equation that involves the derivative of this function s. Such an equation is called the differential equation. So differential equations are incredibly important in science. I can't overstress their importance in science. So many of our important physical laws from chemistry and from physics and from all branches of science are written down as differential equations, equations involving derivatives of functions. And we want to use those equations to determine what the original function actually is, right? So we're often called on in science to solve differential equations, like we solved this differential equation. We knew the second derivative of the function s, so we were able to then figure out what the function s is, okay? But what allows us to solve these so-called differential equations, right, is our knowledge of integration, all right? Okay, so there's one application of integration, but that's a hugely important. It's hard to overstress its importance, okay, to science, and other disciplines too, other than science. I shouldn't restrict ourselves to science. Very important in business as well, okay, and in other disciplines too. All right, so let's stop there. And we're going to continue talking about integration, but let's take a break here for a few minutes. So we'll come back at about 12:45, and we're going to sharpen our integration skills a little bit, okay? Because so far we've been just focusing on almost exclusively on the anti-power rule to help us with integration. But you know, there are lots of other, and the anti-power rule is the opposite of the power rule, but there are lots of other rules that we use to help us with derivatives, right? Okay, like the product rule or the chain rule. So what is the reverse of the product rule, for instance? What does that look like when we run that in reverse? Or what is the reverse of the chain rule? What does that look like when we run that in reverse? All right. Well, we're going to start with the chain rule. The product rule is a little bit harder. We'll start with the chain rule. What does the chain rule look like in reverse? All right. So Okay, so let's pause there and then we'll come back at 12. Okay, I restarted the recording, so I hope everyone's there. If you're not there, come back. I want you to pay kind of close attention to what I'm doing here for these final 30 minutes, because this is really important. Okay, so I have some earlier examples in these notes, but we'll go back to those earlier examples. They're a little bit simpler, and I want to, before I quit today, I want to show you the little bit more challenging examples, because as I mentioned before the break there, what we're talking about in these examples is how does the reverse of the chain rule look in practice, right? Because we often use the chain rule and other rules as well, but we often use the chain rule to help us find derivatives. And so that means if we're trying to find any derivatives, we're going to be running into situations where, we're kind of looking at formulas where the derivative was found by the chain rule. And so when we find the antiderivative, right, we kind of are thinking of running the chain rule in reverse. So what do those situations kind of look like? And how do we sort of run the, work the chain rule backwards, right? How do we find the antiderivatives of derivatives that were computed using the chain rule? Okay. All right. So, again, I might have mentioned this before I started the recording at the beginning of the class, if you were a little bit late. Remember, if you took the makeup test, I graded those and I mailed those back, and I adjusted your scores in WebAssign, right? So you may have a new test score in WebAssign if you scored enough points on the makeup to qualify for the extra points. Okay. So most of you did, and so you should see a higher, if you took the makeup, you probably will see a higher score in WebAssign, and that's probably changed your overall course average too, right? In some cases, for some of you, that might be pretty substantial. All right, so that's good. All right, so okay. All right, so let me show you the two situations that you want to be looking for, okay, when you're trying to find antiderivatives that are going to involve the kind of working the chain rule in reverse. All right. So if you have an integral, all right, where you have an expression raised to a power, okay, where you have an expression raised to a power, that's a situation where we're going to be able to integrate by sort of doing the chain rule in reverse. All right. Now, look, remember, if you have just the variable x raised to a power, you can integrate that just using the anti-power rule. So what I'm talking about is, if you notice in your integrand, if you have not just x raised to a power, but a more complicated expression involving x, that is something that you want to be looking for. Okay, so if you had some formula raised to a power, not just x raised to a power, all right, then that's something that you want to observe. That's a kind of a trigger that you want to look for when you're integrating. Okay, the other situation that you want to be looking for is if you have a trig function of an expression. Not just x, not just sine of x or cosine of x or tangent of x, but if you have a trig function of some formula that's a little bit more complicated than just x, okay, that is a situation that you want to be looking for in integrand that you're trying to integrate. Okay, so if those two, so it requires you to have a little pattern recognition power here, right? To be a little bit observant. Again, when you're in your integrand, the formula that you're trying to integrate, if you notice that, oh, I have an expression, some formula raised to a power, okay, that's something that you need to watch for, okay? Or if you have a trig function of some expression, not just x, but some expression that involves x, some formula that involves x, right? That's another situation that you want to pay attention to, okay? All right, so let's start off with an example. I'm going to show you how when these situations occur, what it is that you want to do, okay? But this example is going to be kind of pretty straightforward, obvious, because it's the first example that we're looking at, right? So when you first look at the example, you're thinking, oh my God, this is a terrible antiderivative I'm expected to find, right? Okay, so here we want to integrate 2x times x squared plus 1 squared, okay? And then, of course, we just have the dx thrown in there, right? Because that's kind of mandatory. All right, so look, when you first look at this, it looks overwhelming. This looks like it's going to be very difficult to integrate, okay? And it could be kind of hard to integrate. Actually, there are multiple ways we could go about doing this integration, okay? But the key thing here is what I want you to look for is, look, here you have this expression, right? X squared plus 1 raised to a power. That's what I want you to sort of focus on, right? Is we have this expression raised to a power, okay? So that's exactly right what I was describing earlier of kind of a trigger, right, that you want to look for. You don't get hung up here on the 2x being multiplied in, okay? What you're really trying to key on here is, oh, I've got an expression raised to a power. When that situation occurs, okay, then here's the trick that we're gonna use that sometimes works and sometimes it doesn't work. I gotta warn you, sometimes it doesn't work, okay? But it's something worth trying. Saad, did you have a question there? Okay, so here we have again, we have this expression x squared plus 1, right? Okay, and we notice that it's raised to this power. All right, here's what I'm going to do. Okay, here's the process that I'm going to go through. And again, it's not clear why this is the case when I'm actually doing this, but what we're really doing is we're reversing the chain rule. All right, this is what we're really going to be doing here. All right. So what I'm going to do now is I'm going to simplify this integrand a little bit in the following way. All right. So again, the expression that was raised to the power is x squared plus 1, right? Not interested in the power. It's the expression that's raised to the power is x squared plus 1. I'm going to give that a different name. So I'm going to say, let's let u be x squared plus 1. So I'm going to kind of change the variable here in this problem. All right. So I'm going to let u, this variable, be equal to x squared plus 1. All right. Now, of course, when you make that substitution, of course, that makes the integrand look different, right? So now you have 2x times, remember the x squared plus 1, I'm going to call that u. So I have u squared, and then I have now the dx. All right. Now, when I make this substitution, for the x squared plus 1, I mean, I can do that, all right? But notice that what's happened here is, well, it does make the integrand look a little bit easier, right? Okay, because now instead of having all of this x squared plus 1, now I just have a u here, right? But unfortunately, what I've also done is I've mixed up variables in my integrand. Now instead of just having one variable, now I have, unfortunately, 2 variables, right? That I cannot have. All right. So I either need to have an integrand with just u in it, or I need to have an integrand with just x in it, right? But I can't have the integrand here with both u's and x's. That's not going to work. All right. So what I'm going to try to do here is get rid of these other x's. All right. Now here's how I'm going to do that. All right, because I don't want to have again a mix here of variables. All right. So look back up here where you let u equal x squared plus 1. I'm going to take the derivative of u. I'm going to take the derivative of u with respect to x. So let's write that down. I'm going to take du dx, the derivative of u with respect to the variable x. I'm not going to write u prime. I'm not going to use the prime notation. There's a reason for that. I'm going to use the old-fashioned du over dx notation. All right, Saad, now you help me here. What is the derivative, of course, of u? What is the derivative of 2x plus 1?
Two x plus 1, so that would be
I'm sorry,
two.
I said it wrong. What's the derivative of x squared plus 1? What did you say?
So it would be 2x.
Yeah, 2x, right? Okay. I think I gave away the answer when I was talking there. I was thinking ahead, right?
Right.
So du dx now is 2x, right, Saad? Now, Saad, what I'm going to do here is solve. So this is kind of strange now. I'm going to solve this equation for dx. I'm going to treat that dx kind of like it's a variable, and I'm going to solve this equation for dx. So I want to rewrite this as dx equals something. Okay. All right. Now, how can I do that? So how can I solve this equation for dx? Well, first thing you do here is multiply both sides of the equation by dx. Okay. So multiply both sides by dx. Of course, what happens on the left-hand side here? When I multiply both sides by dx, what happens here on the left-hand side? What happens over here to the dx's?
The bottom, the dx cancels out, so you only have
right. Yeah, the
this
dx's cancel out,
topic.
right?
Yeah.
Okay, and so you get du is 2x times dx, right? And now just divide both sides by 2x. Divide both sides by 2x. And of course, here the 2x's cancel, right? So you get what you wanted. You get dx is equal to 2u over, du over 2x. So I solve this equation for dx. Now, why did we do that? Well, let me show you. Because now I'm going to take this, because that's what dx is equal to, right? And I'm going to substitute that back into the integrand, or dx. See, I have dx in here. So I'm going to plug now du over 2x. So this looks really mysterious why I'm doing this, but let's see what happens. So I have u squared times the dx, but now I know the dx is this. It's du over 2x. All right, now what have I achieved by doing this? Well, something really nice happens here. Look what happens to the 2x's here. They divide out. Isn't that crazy? The 2x's divide out, and look what you're left with here. You're left with just u squared times du. That's just a real simple integral, but involves the variable u, not the variable x. But now you can integrate this, right? Okay, because you're just integrating u squared. That's an easy integral because you can just use the anti-power rule here. What is the antiderivative of u squared? What does the anti-power rule say the antiderivative will be here? What do you do when you have just your variable raised to a power? What do you do with the power?
You add 1 and then divide it over 2 plus 1.
Yeah, so which is 3, right, Alpha? So you get here u cubed over 3, and then don't forget your constant, right? Okay. Now, however, so there's actually the answer in a sense, but of course, what's bad about that answer is that answer has u in it. And remember, our original integrand had x in it, right? So now I want to switch back to x's. How do I get back to x's here? Well, you just have to remember, what was u? U was x squared plus 1, right? So I'm going to put back in for u x squared plus 1. So we have x squared plus 1 cubed over 3 plus the constant. There is my answer.
I'm so scared. It's been 24 hours.
Okay.
Don't be mad at me. I'm sorry.
Whoops. Someone's talking. Got your mic on. All right. Y'all see the answer here now? Here is the answer. It's x squared plus 1 over to the cubed over 3 plus the constant. So we end up with not really a bad answer, right? Okay. But we did have to go through this intermediate process here of substituting the u for the x squared plus 1. This process where we made that substitution is called integration by substitution. But what it really is it's the reverse of the chain rule, all right? So integration by substitution or the anti-chain rule, okay? Wow, all right, so that's kind of different, right? Okay, let's try it again. I think we have just enough time for another nice example. This one involves trig though, okay, instead of a power. All right, so remember, I said what you're looking for are these two situations, okay, where you have trig function of an expression, not just x, but some expression involving x, or you have an expression raised to a power. That's exactly the situation we have in this integrand, right? We have cosine of, and now we have an expression. We don't have just cosine of x. We have an expression involving x. It's 5x, all right? So this is going to be a perfect opportunity for us to use the anti-chain rule or integration by substitution, all right? So how do we figure out how the substitution works? Again, what you're keying in on here is that you have cosine of an expression. What is that expression? Obviously, someone. We have cosine of what? Daniel, are you watching there? Cosine of what here?
A power?
Yeah, no, it's just cosine of, you just have to kind of read it back to me here. Cosine of what thing, right? What expression do we have cosine of?
5x.
Yeah, 5x, right, okay. If this were just cosine of x, this would be something different, okay? But this is cosine of 5x, all right? So it's an expression involving x, not just x. So the way you start the substitution is pick u. It doesn't have to be u. You could use z or some other variable, but kind of the usual choice there is u, all right? Let u be equal to that expression, okay? Since we had cosine of 5x, we'll let u be equal to the 5x. So again, if you have a trig function of an expression, substitute for the expression. Or if you have an expression raised to a power, substitute for the expression again. All right, so if I say u is equal to 5x and I make that substitution, here's what I have. I have 5 times cosine of u and then times dx. But again, remember, the issue here is, unfortunately now I've got different variables in my integrand, right? Here I have a u and here I have an x. The d doesn't count as a variable, by the way, okay? So I can't have that, right? I cannot have multiple different variables in my integrand. I've got to settle on one variable, and the one we're going to settle on here is u. That was the whole purpose of making the substitution. So somehow I have to get rid of this dx, right? Okay, I cannot have dx here. But remember, what's the trick for getting rid of the dx? So what's the game that we play here? You go back to this substitution and do what? What did we do in the prior example? Alba's been helping me all the time. Someone else, Lance or Colin or someone, Donna.
I'm a bit confused. I need to be reminded.
Okay, well, up here, all right, see, once we had made this substitution, right? Okay, then what did we do? What was the next line
Oh,
there?
you took the derivative of it? Or?
Took the derivative, right? Take the derivative. So take the derivative of u with respect to x. You're always going to do it with respect to x, okay? So
That's 5, right?
that's right. That's easy. That is 5, okay? Now solve this equation for dx. So treat dx like you can separate it from du and solve this equation. This is where the old-fashioned notation really turns out to be useful, all right? So how do I do that? Well, multiply both sides by dx. That's how you would start. These dx's will cancel, and so you have du is equal to 5 times dx, but I really don't care what du is. I want to solve for dx. So now divide both sides by 5, all right? So you get dx is equal to du over 5. And that's what you're going to plug in for dx up here, so you can get rid of the x, because you can't have, again, these multiple variables here. So what happens when I do that? I have 5 times cosine of u times what's dx? That's du over 5. And now by some miracle luck here, Colin, look what happens to the 5s.
They cancel out.
Yeah, it seems almost unbelievable, but they cancel out. So I kind of was ignoring the 5 there at first because I was hoping exactly this would happen, and this is what happened, all right? So, Colin, you end up with this integral. It doesn't have x in it. It's got u in it, but that doesn't matter, right? Okay. I mean, that's just a changing a name. You end up with this integral. We want to integrate cosine of u. God, I bet you know what that is. What is the antiderivative of cosine?
It's a sine.
Sine, right. So this is just sine of u, not x, because now we've changed things to u, plus a constant. So notice the integral sign is gone because we've taken the antiderivative. So see, we've made progress. The only last thing we have to worry about here is, darn it, I don't want u because the original problem had x in it. So I've got to get back to x. But that's easy because what was u equal to? By our own choice?
5x.
Yeah. So all you have to do is replace the u with 5x. So there finally is your answer. Just sine of 5x plus a constant. Nice, right? So what looked to be a terrible, not terrible, but a little bit more complicated antiderivative, actually not that bad, okay? Because we sort of converted it to just cosine of u, which is easy antiderivative, right? I mean, we can do that by just guessing at what the
Can I ask
answer
a question?
Yes.
So let's suppose we take the derivative of sine 5x plus c, right? That just involves the product rule, right? So it's just 5.
No, it doesn't involve the product rule.
Okay.
What is the derivative of sine of 5x? It's going to be what?
Cosine.
Cosine of 5x. But then you have to remember, since this is 5x, not x, what do you have to multiply in here?
Yes, that's right. The derivative of 5x is 5.
Ah, yes. See that? So the chain rule was involved there,
That's what I
right?
meant, chain rule.
Yeah, that's the chain rule. And that's why I was calling this process here is really reversing the chain rule. So we can think of this integration as the anti-chain rule, but we never really think of it that way. We call it integration by substitution, but integration by substitution is really reversing the chain rule. Okay. Let's set up the next one. I don't think we can go all the way through it, but you guys can tell me how we're going to do integration by substitution here. Here I'm trying to integrate the square root of 2x minus 1, right? Okay, so let's first convert that square root to 1/2 power, because that's what we always do, right? So we're going to convert the square root to 1/2 power. So we have this 2x minus 1 to the 1/2 power. And now here's this is the key thing you have to notice. So this is really the hard part of the problem. The rest of the problem is really just algebra and arithmetic. The hard part is noticing, here I have an expression. It's not just x. I have an expression raised to a power. Oh, when I have an expression raised to a power, that's an opportunity for substitution, right? If it were just x raised to a power, that would be easy to integrate. You would just use the anti-power rule. But here, it's unfortunately a little bit worse than x. It's 2x minus 1 raised to a power. So I will do substitution. And the substitution I'm going to use is I'm going to substitute for this expression. So let's let u be 2x minus 1 so that I can get just u raised to a power. See, I don't have a complicated expression raised to a power. I just have u raised to a power. Unfortunately, hanging around is the dx after I make this substitution. So I have to get rid of the dx. How do I get rid of the dx? What's the game? So this is kind of a little game you play. How do you get rid of the dx? What do you do with this? Dan, what do you do with this? Lance, someone? Oh, guys, if y'all aren't watching, y'all are in trouble. What do you do with this, Lance?
Derive it.
What now?
Take the derivative.
Yeah, take the derivative. So I get what? Du dx equals, this is
Just
so
2.
easy here. What?
Just 2.
2. And then solve this for dx. Well, let me solve that for dx for us. So just quickly, you're going to end up with dx equals du over 2. So here is really what I'm integrating. 1/2 times du over 2. Now, unfortunately here, the 2 does not cancel. So what can I do with the 2? So that's the mystery there. What can I do with that 2? Because what I would like to be integrating is just u to the 1/2 times du. So what can I do with that 2 in the denominator so that I can end up here with just u to the 1/2 times du? Because that's easy to integrate, right, Lance? What is the antiderivative of this?
Could you for the 2, could you like factor it out and put it in front of the integral sign?
That's exactly what we can do, right? Yeah, okay. We're going to factor that in front of the integral sign. Yeah, okay. So we'll talk about that next time. So the 2 is really easy to deal with. We can just factor that out in front of the integral sign. How does this integrate now? Once we've sort of dealt with the 2, no matter how we do that, Lance, how does this now integrate?
It's just it's going to be 2 over 3 u to the power of 3 over 2.
Yeah, so it's so you actually did it very fast there. It's u to the 1/2 plus 1, which is 3/2 over 3/2, and when you divide by 3/2, that's same as multiplying by 2/3, right? Okay.
Yeah.
So we know our answer is going to look something like this, correct, right? And then we just have to undo this substitution. So we have to plug back in the 2x minus 1 for the u. So the only question we have to answer here is, what happens to this 2, right? Okay, how do I deal with that so that I can make this antiderivative like this, right? Okay. All right. Well, so you already mentioned, Lance, what the secret is, but we'll talk about that formally next time. Okay. But it's easy. All right. So we've run out of time for today, right? Okay. So that's a lot to process, this integration by substitution, right? Okay. So we need to see plenty of more examples of doing that, but it is just a step-by-step process. All right. So it's not an impossible process. You just have to follow the steps, but you do have to recognize when you're going to initiate doing the steps, right? Okay. That is the key thing. Okay, so no homework due till Thursday, right? But make sure you're keeping up with your homework, right? So I'll see you guys again on Thursday, okay? So I'm going to stop the recording.